Welcome to this next lesson. We're going to take a look at the energy coming from the sun and the energy from Earth too, because these things are both important to how energy flows in Earth's climate system, and in particular are important for understanding the greenhouse effect. Just about everything radiates energy. The walls of your room, your furniture, the plants in the park, your food, everything around you. The sun gives off energy, and some of that energy travels through space to Earth. The Earth gives off energy that eventually travels back to space too. But what types of energy and how much energy do the sun and the Earth give off? In this lesson, we're going to learn and apply two physical principles, both having to do with the energy radiated by different things. The sun is, of course, different from the Earth, which is different from a glacier, which is different from you or me or your furniture, and we're all different in terms of the amount and type of radiation each thing gives off. The two physical relationships that matter for us here are first, a relationship between an object's temperature and the wavelengths of energy the object emits. And second, a relationship between an object's temperature and the total amount of energy the object emits. We're going to start with the sun. The sun is the source of energy for Earth's climate system, and it gives off a measurable amount of energy with a measurable range of wavelengths, both of which are dependent on its temperature. We're going to go at this a little bit backwards and think about how we might take the sun's temperature. We can't just go stick a thermometer in it like we could to take our own temperature, but what we can do is measure characteristics of the electromagnetic radiation coming from the sun and then use physical laws to figure out the sun's temperature. Here's a quick review of the electromagnetic spectrum. Electromagnetic energy comes in different flavors, with different wavelengths, frequencies, and photon energies. For our purposes, we're primarily interested in wavelengths in the visible range, the infrared, and a little bit of ultraviolet. Of these, ultraviolet has the shortest wavelengths, highest frequencies, and highest photon energies. You already explored that in a reading. To get warmed up, let's try a couple of questions. Which of these stoves is the hottest? If you said C, you probably have some experience with electric stoves like mine, and you know it's probably not a good idea to put your hand down on a red burner because it's hot and it's giving off a lot of energy and you might get burned. A black burner is definitely cooler than a red burner. So there seems to be some relationship between the stove color, the temperature, and the amount of energy the stove gives off. Try this question next. This one's a little harder. Which of these stoves do you think is emitting radiation with the longest peak wavelength? Think about what part of the electromagnetic spectrum would correspond to the emissions of these three stoves. Stove C, we can tell, is red. It's emitting some radiation in the visible range, which human eyes can see. Stove B, however, is black here in this picture, which was taken at room temperature. That stove is emitting radiation at wavelengths that we can't see. These wavelengths are in the infrared part of the spectrum, which are longer wavelengths than visible light. Infrared is the same range of radiation that you and I also emit. We're not actually hot enough to emit visible light. If we were able to crank up the temperature on these stoves further, the elements would get brighter and might start emitting light in the yellow part of the visible spectrum at shorter wavelengths than the red. So let's apply that idea to some stars. Which of these stars is the hottest? Star A looks like it's mostly emitting red light. Star B looks like it's mostly emitting blue light. And star C looks like it's mostly emitting yellow light. Thinking about the electromagnetic spectrum, red is at the long wavelength end of the visible range, yellow is in the middle, and blue is at the short wavelength end. So, just like the stoves, the star that emits the shortest wavelengths is the hottest. And in this example, that's star B. Here's the electromagnetic spectrum again, which can help us see that the blue star emits shorter wavelengths than the red star. So this is pretty cool, and we can use it. There's even an equation for it. A fairly long time ago, some physicists, notably a person named Wilhelm Wien, figured out the relationship between an object's temperature and the peak wavelength of radiation that it emits. In the equation here, the T stands for temperature, and that's on the Kelvin temperature scale. The lambda with the little m next to it stands for the peak wavelength emitted in units of micrometers. And then the W is a constant that Wien figured out by doing a lot of observations. You might not like equations very much, and we won't have very many of them, but this is one that's important. The key thing to note here is that if temperature goes up, the wavelength of maximum emission goes down. Hotter objects emit radiation at shorter wavelengths, just like those stoves and those stars. Getting back to our question about the sun's temperature, this equation lets us figure it out. We can save ourselves a trip to the sun by measuring the peak wavelength of the radiation coming off the sun, then using Wien's law to calculate the sun's temperature. So we do it. We measure the spectrum of electromagnetic radiation emitted by the sun, and we find out that the sun's wavelength of maximum emission is in the visible range. Not surprising, you probably knew that. And more specifically, the peak is at about half a micron wavelength. That's the peak or wavelength of maximum emission in Wien's law. Of course, the sun also emits radiation all across the visible part of the spectrum, and also emits ultraviolet and infrared radiation, but those are on the sloping sides of its emission spectrum. Okay, with a peak wavelength of half a micrometer, we can now use Wien's law and figure out the sun's temperature. After a little algebra, we find out that the sun's temperature is close to 5,800 Kelvin, which is pretty hot. So, what about Earth? You can see here that the spectrum of radiation Earth gives off is out in the infrared at longer wavelengths, which is expected since we know that the Earth is cooler than the sun. So let's try a question about that. At the top of Earth's atmosphere, the planet emits infrared radiation at a peak wavelength of about 11.4 micrometers. What temperature does that correspond to? From Wien's law, we find out that the temperature at the top of Earth's atmosphere, where energy is radiating to space, is about 255 Kelvin, or choice C here, which is about the same as minus 18 degrees Celsius, or about 0 degrees Fahrenheit. It's pretty cold up there. So we've determined that the sun and Earth give off different types of energy, which is going to become important when we talk about the greenhouse effect. But also, as you can probably imagine, every square meter of the sun's surface emits tremendously more energy every second than every square meter of Earth emits. This is the other important law relating temperature and energy. This one was figured out by two people, Stefan and Boltzmann, so it's the StefanBoltzmann Law. This relationship says that as temperature increases, the amount of energy given off by an object per second, per area, goes up exponentially to the fourth power. So for example, if you double the temperature, the energy given off per second per square meter doesn't just double, it goes up by 16 times. So it goes up a lot. Recall that the energy per photon is higher for shorter wavelength, higher frequency radiation, like ultraviolet radiation. Thinking about Wien's law, as something gets hotter, it emits shorter wavelength radiation, which has higher energy per photon. The StefanBoltzmann law takes into account that increased energy per photon at shorter wavelengths. If we actually do the math, and I'd encourage you to try the math, we come up with the answer that each square meter of the sun's surface gives off about 64 million joules every second. In contrast, the Earth's upper atmosphere gives off only about 240 watts per meter squared. Just imagine those boxes drawn on the sun and the Earth as only 1 meter square. All right, key points from this lesson. The sun is hot. Because it's hot, it gives off lots of energy per second per square meter. Much, much more than Earth gives off. Also because it's hot, the sun gives off radiation at visible wavelengths, and Earth, because it's cooler, gives off radiation at infrared wavelengths. The primary reason to spend time on these relationships is so we can use them when we have a look at the different types of energy transferring around within Earth's climate system, which is coming up in later lessons. To close this lesson, wherever you are, take a look around you, pick up 4 objects, and rank them by their wavelength of maximum emission, and the energy they gave off in watts per meter squared.